morning. So Joshua has been a former colleague, and as I said, started as a student. But I will formally introduce Joshua. Joshua holds a PhD in industrial engineering and a Master of Science in mechanical engineering from the University of Cagliari in Italy, focusing in safety and energy systems. Joshua deepened his studies into the numerical fluid dynamics with a postgraduate course at von Karman Institute. His main topics have been the CFD modeling of the wind solving the Reynolds-Navier-Stokes equations and with large eddy simulations. In the period from 2007 until 2013, Joshua was working as a software developer and wind analyst in WindSim. Among the scientific topics of interest were the wind characteristics over forested areas and the actuated disk modeling. Today, Joshua holds a position as a wind analyst and safety engineer at NL Green Power. So, Joshua, can you take control of the screen and run your presentation, please?
Yeah, thank you very much, Arne, for the introduction. I will try to. I should be able to share my screen.
That was the idea.
Let me see. Are you able to?
Yes, we can see it.
Okay, perfect. Then I proceed in this way. Yeah, use of sector-wise Money-Nabokov-Land settings in a wind resource assessment study. A method to account for variable stability conditions with wind direction. So I'm going to talk about a case study we had in NL Green Power, and see if there are some takeaways from this presentation. So the site, first of all, is very complex and is widely covered by trees. So it's forestry is very present, and there is a presence of 5 met masts in the area. What you are going to see also in this presentation is a classification method of stability conditions based on the Money-Nabokov length, and also a methodology based on cross predictions between masts to evaluate, to quantify the goodness of different WindSim projects on the same locations, so varying settings. And in particular, I saw the neutral flow model. So without activating the energy equation, thermal flow with and without canopies. Then we construct these cross prediction matrices. We extract root mean square error and mean absolute error as a matrix to quantify the goodness of the performance with one single matrix, and try to drive to conclusions. So I will end these presentations with conclusions and some tips for WindSim. Yeah. So the site is complex orography. Is basically is done of a complex system of ridges and valleys in this at altitude of between 200 and almost 900 meters. An escarpment is present on the north side, and north of our escarpment is almost flat, the terrain. Forestry is present more or less everywhere, besides some clearance points. but mostly is forested. And we are gonna develop the area in the south part, so the most complex part. The masts are 180 meters tall, and while the hub height of the future turbines will be 149 meters. The met masts are spread more or less in a scattered way along the development area, with an average distance between the mast of 9 kilometers, a minimum distance of, let's say, 4.5 kilometers, and a maximum distance of 15.4 kilometers. Okay. So we use the series products from Vortex, initiated with ERA 5. And normally we use the 20 years data. In the newest version of this product, there is a new column, which is the reciprocal of the Money-Nabokov lens. So I use this data, source of data, to start classifying the time series based on actually on the classification, which is present also in the description pages of WinSim. So the ranges of Money-Nabokov lens are the one that you can find also in the description pages of WinSim. And you can see in a pie plot, or but basically we split into, let's say, into important classes. So merging the stable cases, so between 0 and 1000 meters, and everything that is not stable. So neutral and unstable, everything merged in one other big class. Only from the records classified as a stable, we computed the Money-Nabokov lens sector by sector. And we repeated this statistics for each mast, and at the end we made an average. So for at the end we had one average value of Money-Nabokov lens per sector only for stable cases. So the Money-Nabokov lens assigned to each sector in the wind field, but I mean here we had to evaluate somehow the Money-Nabokov lens to use in the simulations, because as WinSim is now, you can give only one value of Money-Nabokov lens per sector. And so the numbers to introduce in the GUI, in the interface, I use this simple formula. Well, I rounded to 100 meters. What? The weighted average of 1000 meters taken for the not stable cases. So 1000 meters multiplying the frequency per sector per unstable and neutral, plus the frequency of the stable cases, which is multiplying the average that I calculated before, only for the stable. So I end up with a value of Money-Nabokov lens that generally is could be the typical of a lightly stable, but this really depends, of course, site by site. It could be also smaller if the frequency of the stable cases is quite important. So but in this way, we have values of Money-Nabokov lens to assign to the GUI in the wind field module, which will vary sector by sector. And but then how to say which is to quantify which is the best set of settings? No, you have to use some key performance index. No, so what we do in ANAL, the energy calculation, the final energy calculation is not performed in WinSim, is performed in OpenWind. So actually what we do in WinSim is to generate a WRG. We export the WRG actually for each mast and also weighted against all the mast. But for constructing this cross prediction matrix, we use the WRG exported for each mast, read in OpenWind, and then adjusted adjusted to the generating mast. This just to in order to have in the matrix a diagonal made of zero. So each mast self-predicting, so predicting itself will be zeros. Normally, there are some probably extrapolation, interpolation errors in the construction of the WRG and in the reading of the WRG, and the diagonal will not be made of exactly zeros values. This is something that we introduce in our procedure, but we have to investigate further if it's what will be the right thing to do. So basically, we have a matrix of mean wind speed. We construct first a matrix of wind speed predicted at all the masses starting from the predictors. So from mass 1, 2, 3, and 4, 5. And then starting from this, we calculated the percentage error on, because we know the true value, the mean wind speed measured at the target. And from a matrix, we obtain a scalar by doing an average so the root mean square error and the mean absolute error. We can do this taking into account the diagonal, which will lower the value, or without taking into account the diagonal. I'm adding this some comments on the fact that we had to do this adjustment, but there's some work in progress in understand how to improve the cross prediction errors, let's say, the self prediction, so the values in the diagonal. Maybe this is not the right location to put, but actually we tried. We made some proposal already to the support, try to speed up this export of the WRG by decoupling, for example, the exporting of RSF and WRG, and maybe it could be useful to have RSF at the turbines locations. Jump into the comparison of different models. So we use the root mean square error and the mean absolute error of the cross prediction matrices to compare models. So different flow models, and basically is the WRF coming a WRF model coupled with let's say the linear model of OpenWind, which is called the WindMap. It's basically a potential flow model. And so we have a WRF coupled with the WindMap with the potential flow alone, and then WindSim neutral and WindSim thermal. And for each, so for neutral and thermals, also we activate and deactivate the canopy model, and the canopy model made use also only of the C2 drag coefficient. In this project, I mean, of course, this is not from one single project. You cannot draw general conclusion, but in this specific project, we managed to get to the energy equation using the this MOL calculation that I explained before, and without the use of the canopy model. And the canopy model, it's I don't know, it's quite a delicate, let's say, tool, because the results are very sensitive to the parameters. So I think that anytime you activate the canopy model, we should be very confident on the settings. So sometimes it is more, in this case it's more performing just the roughness map without canopy model. And we got a large improvement by using the energy equation. Conclusion, some I've already said. So a new methodology to estimate the Money-Nabokov lens parameter to be assigned to the wind field module has been tested. The methodology accounts for varying MOL sector by sector, and it is based on a weighted average of stable and not stable conditions. It is also presented a criterion to classify performance of flow models in a wind development area, counting several met masts. Those WindSim models showed a significant improvement from neutral flow to thermal flows with Money-Nabokov lens computed in the presented way. The use of the canopy model for the forested area did not bring any improvement to the CFD simulation. In brackets, I evaluated the C2 starting from the trees species, so using the Excel files provided by WindSim. So I knew the species of the forest. Probably another improvement could be brought by running 2 or more levels of stability per sector. So this could be an idea for the future. If we have only 2, for example, could be stable and not stable. And but then for making the post-processing, you would need to assign a frequency to each of these stability conditions. Here, for example, the not stable cases could be modeled without including the energy equations, treated like neutral. Some other tips. Yeah, so again, give also the possibility to give in the GUI variable moles. So, for example, we want to run 3 sectors. It would be nice to have a list of Money-Nabokov lens. Just put 150 down, 3 different numbers, and they'll be associated one by one to the sectors or cases we want to run, or cases in the case of meso-micro coupling. Yeah, I didn't test it yet. MOL computed from local measurements. I can, this I already said, give the possibility to introduce more Money-Nabokov lens per sector. Yeah, here could be clustering data or leave it open to the user to give more Money-Nabokov lens per sector, but this will imply also post-processing. And also it would be nice to have an exporting of the WRG that will not last so long. Maybe there is room for improvement. One improvement could be separated WRG and RSF export. And also I need this worthy to verify if it can be speed up the algorithm for the WRG export. I also saw that the GCV parallel, it seems to me that is not as numerical stable as the serial GCV. At some time, and the serial GCV, so with one CPU can be faster than the parallel GCV, for example, with 2 CPUs, no? So I think there is, and I saw that the GCV serial is faster in some project that I've seen of the iPress serial, so the iPress serial, so with one CPU. So it looks to me that the improvement in the rate of conversion is given by the parallelization. So I believe that it's worth it to see if there is any issue in the parallel GCV, because I think that it could be even faster than the parallel multi-grid. But this I think is worth it to investigate further. And this ends my presentations. So I go back to the chat. I was in full mode and I couldn't see the question. So I see. Is Nicolaus, is there a reason you did not use the WRD and decide to use the WRG when importing into OpenWind? I tested WRB, but had some issues in the import in OpenWind. I don't know if Nikos has some experience in importing WRB in OpenWind. Maybe I was doing something wrong, so I gave up using the WRB, and then I was working now with the WRG. But maybe it's worth it to check again. I see Andres is also asking for the cross prediction in non-canopy models. Have you considered any displacement height at mast, or have you just used the same measurement height in all of them without any displacement? No, I didn't consider any displacement height at the mast, and I didn't even modify the terrain trying to introduce a displacement height. How many Monin-Nabokov lens classes did you finally use? Did you include also the neutral class? Basically, due to the, let's say, the limitation of WinSim, that it will ask only for one value of Monin-Nabokov length per sector. I constructed this methodology, no, where so weighting the MOL from the stable, maybe, and sorry, not stable cases. So I made a weighted average of stable and not stable cases, and then I gave only one value of MOL per sector, and then it was changing sector-wise. So there was not. Only in one case I ran a neutral class for a sector, which was really dominant. The MOL calculated was close to 1,000, so I decided that sector could be run without the energy equation. Yeah. Okay. Maybe I'm still sharing the screen. I don't know.
Yes.
Yeah. There are questions to WinSim. I think there is a question to the.
Yeah. Are we back? Maybe we should share our screen again. Okay. No, there is a question about whether it's possible to generate flow res files, that's the export to EMD, with individual stability conditions for each sector. We have just picked up again after some small pause the communication with EMD. So we are looking into this to make it kind of an easy and streamlined process to do the flow res export and also the flow rec import. This is our ambition, but that's not done today. Okay, so thank you, Joshua. We see, of course, that the use of the energy equations is picking up year by year. Now you have showed us that there are data sets out there that could be used for the classification, and you have also demonstrated how that is working. And thanks for the tips. There are for sure maybe some small things that we could do that would improve kind of the user experience running these cases with variable Monino-Bukov length. So thanks for that.
My pleasure.
Before we